Morning, everyone. Welcome to the morning session. And the first speaker is Professor Matthias Gaberdiel from ETH Zurich. He is well known for his work on high-spin theory and CFT. And today he will talk about process with AdS3 and CFT2. Let's welcome.
Well, thank you very much, and thank you very much for the invitation to come here. It's, again, a great pleasure to be back. So I'm going to want to talk to you about the recent progress with AdS3 CFT2. So I'm not going to review in great detail but the sort of the paradigm example that we believe we understand now in great detail, which is one incarnation of AdS CFT you can de facto prove, where you have AdS3 cross S3 cross T4 with a specific background flux. So this is a background that's very, very small, where the AdS size is string scale. So this is very difficult to describe in supergravity, but you can hope to describe it in string theory. And we found a solvable worldsheet theory that's effectively free. And we proved that this is exactly due to a two-dimensional conformal field theory, namely the symmetric orbifold of T4. And when I say proof that it's exactly dual, what I mean is that we showed that the spectrum agrees. And by that, I mean the full spectrum, not just the BPS spectrum, all the single particle states. And furthermore, we showed that the correlators on this side are reproduced by this side. So this is, okay, it's probably not a mathematician proof, but to a physicist, that is effectively a proof of the correspondence. You show that the states match, and you show that the correlators match. So this is by now well known, and I don't want to dwell on it. What I want to explain to you today are two more recent developments where we've been trying to go away from this very special point. Now, it's nice to have one specific incarnation, but it's a very specific incarnation, and it's one that doesn't have any Ramond-Ramond flux. It works for pure Neveu-Schwarz flux. And this is nice in AdS3, but if you think about trying to generalize it to AdS5 cross S5, then in AdS5 you will have to switch on Ramond-Ramond flux because there is no analog of NS-NS flux. So you will have to understand how will this work if you have Ramond-Ramond flux present. And in this context, there's a canonical way of trying to understand this. And this is by switching on Ramond-Ramond flux, which is a continuous parameter in this background at the weakly coupled point. So what I'll explain to you is that we understand now the theory as you perturb away from this special point. We've shown that this perturbation is integrable from first principles by doing a first principle symmetric orbifold calculation. And it has helped to shed light on some of the old questions that people had conjectured about how exactly the space-time magnons are represented from the symmetric orbifold point of view. And I'll explain to you in more detail later while there is a puzzle. At least there was always a puzzle for me. And now I feel I understand the answer. And it's not that I just understand the answer. I can calculate the answer and see what happens. And that's the first half of what I want to explain to you. Now, the second half is the graveyard of all AdS CFT proposals. It's the string duality for AdS3 cross S3 cross S3 cross S1. This is not just a mouthful to pronounce. It's also the one theory for which there are many wrong proposals into literature, I believe. And what we believe is we finally found the correct version, but I should be very careful. Time will tell whether it's really true, but I believe we have now managed, and this is very recent work I've done together with Lorenz Eberhard, following work I've done with a student of mine, in that we can prove the AdS CFT duality for AdS3 cross S3 cross S3 cross S1 to the same extent that we could prove the original duality for AdS3 cross S3 cross T4, but it works slightly differently than what we had originally in mind. And I want to explain to you what we believe is the correct proposal and in which way we believe we have proven it. And it's actually quite neat because this proposal, as it will turn out, will have a simple description in the NSR formalism. So you won't have to go to this more complicated hybrid formalism. And therefore, in some sense, is in some sense simpler than the AdS3 cross S3 cross T4 duality. But again, it's a corner of string theory where many subtle things happen, but we believe we really managed to prove it. And I want to explain to you what we have done and what our evidence for that is. So please interrupt me. I don't want to overwhelm you with detail. I'm also not going to go into all the technical details. I'll try to give you sort of the gist of the argument. And if you have more concrete questions, please come and talk to me, and I'll be happy to explain them in more detail. So let's start with the first point. So unfortunately, I have to introduce a little bit of technology to explain you what I mean by that. Well, to start with, I give you the general reason why we find this interesting, and this is what I already said. We want to learn how to switch on Ramond-Ramond flux because that's somehow the avatar to 4D superioring mills. And in the context of the symmetric orbifold, which remember is the CFT dual for AdS3 cross S3 cross D4, there's an exactly marginal operator that switches on Ramond-Ramond flux, and you know which one it is. So it turns into a question of calculating the anomalous conformal dimensions in the symmetric orbifold when you perturb that operator. Now, we are not the first persons to realize that, but again, for reasons that I'll maybe hint a little bit at, this is something people have tried since 2002. So there was the paper by Gaberdiel and Gomez, Model, and Strominger. And then subsequently, Rastelli and Razamat and Pachman tried to identify the integrable structure. But this has been complicated. And I think we've really managed to solve it. And I'll explain to you exactly what we have done and what evidence we have found for this being an integrable description and in which sense it reproduces what you may have hoped. Okay, so what is the symmetric orbifold? The symmetric orbifold is you take T4. T4, to a simple-minded person like me, is just 4 free bosons and 4 free fermions. I'm going to ignore largely the momentum and winding modes, but you can take them along. And you don't take one of them because you like it, you take n of them. So you take n tori, and then you divide out by the symmetric group that commutes the n copies of the tori. And that is an orbifold, so there is a standard construction in conformal field theory that tells you what the conformal field theory is that comes from this. And there is something called an untwisted sector, which is basically you take everything you can make from n tori and you look at everything that's symmetric invariant under the symmetric group. But then there are the so-called twisted sectors, and the twisted sectors are associated to the conjugacy classes of the symmetric group. And the conjugacy classes of the symmetric group, as probably most of you know, are just the cycle shapes, because every permutation you can write as a product of cycles, and under conjugation you're not going to change the shape of the cycles. Now, the string theory intuition is that each cycle corresponds to sort of essentially a trace. So if you're looking at the analog of the single trace operators, you want to have one cycle of length W and all the other cycles to be one cycle. So this is the sector I'm going to focus on because that's what corresponds to perturbative string theory on the worldsheet. And the multi-cycle states will correspond to what you get from string field theory, where you're going to look at multi-string states. So we're going to concentrate on the single cycle sectors, and you should think of that as being the analog of single trace operators and super-Young mills. Okay, so I don't want to go into great detail about the single cycle sector. So roughly speaking, they have a BPS state of a certain conformal dimension and SU2 spin. So this conformal field theory is n equals to 4 superconformal symmetries. So at an SU2 affine symmetry, and the BPS condition is that the conformal dimension is equal to the spin. And in the sector with cycle length W, you have a BPS state with these charges. You actually have others as well, but there is in particular one with these charges. And then what distinguishes this W cycle twisted sector is that on top of that, you have fractionally moded modes. So while normally if you expand a field in modes, bosons will have integer modes, fermions will have half-integer modes. In the W cycle twisted sector, everybody gets mode numbers that are fractional in terms of n over W. So n is an integer, W is the W of the cycle length. So you get a spectrum as W gets larger, the ground state gets higher and higher in conformal dimension, but on top of that, you get states that are smaller and smaller in excitation now. So that's the structure of this, the twisted sector of this symmetric orbifold. So you have left movers and you have right movers, and then you have something which is orbifold invariance condition, which you want to think of as being momentum conservation of the string. So you want to think of this fractional number as basically being the momentum of the associated Marknon, if you think, and the orbifold invariance condition is just that the sum of the left moving momenta and the sum of the right moving momenta have to differ by an integer. They don't automatically differ by an integer because they're fractional in units of 1 over W. And that already goes back to the old idea of Gaberdiel. Okay, so this is basically the states in the W cycle twisted sector of the symmetric orbifold. And now we want to understand what happens when we perturb that theory by the exactly marginal operator that corresponds to switching on Ramond-Ramond flux. And this operator comes from the 2-cycle twisted sector, as it happens. So it's not from the untwisted sector, it's from a specific sector of this theory. where the ground state in the two-cycle, you take the ground state in the two-cycle twisted sector, which has conformal dimensional half, and then you take the G descendant, and that gives you an exactly marginal operator. But because it's in the two-cycle twisted sector, purely based on the group theory, you know that when you're looking at the operator product expansion of somebody from the W cycle with somebody to the two cycle, you're going to generate in general W plus 1 and W minus 1, but you're never going to generate W because 2 is an odd permutation. If you start with a permutation with W and you multiply it with an odd permutation, you're going to change it. You're going to W plus 1 or W minus 1 or multi-cycle terms. We are going to ignore the multi-cycle terms because we are doing the large N expansion. So large N expansion means you can ignore the multi-cycle terms. We are currently together with Chang Kang and Beat Naetz trying to understand the structure of the multi-cycle terms, i.e. the 1 over n corrections to our answer. But what we are doing here is leading order in 1 over n, just like you do for n equals to 4 Supermills. So because we are going to end up in W plus 1 and W minus 1, it's convenient to define that operator that is just a bookkeeping device of telling you in which sector you're going to land. And the idea is, following what Niklas Meissert very successfully did for n equals to 4 Supermills, is to understand the anomalous conformal dimension from the structure of the modified structure of the supercharge action on these states. So let me explain to you what I mean by that. So inside our n equals to 4 algebra, we have 4 supercharges, and I'm going to denote them by Q1, S1, Q2 tilde, and S2 tilde. And there are actually double as many, but I'm looking at a subsector, and that's sufficient for all I have in mind, and they satisfy this sort of algebra. So this algebra looks complicated. What's important is that L0 minus K30 is basically the anomalous conformal dimension. So we want to understand the value of C tilde, of Q2 tilde, S2 tilde on a state that will tell us sort of how much the conformal dimension has changed. K3 is the Cartan generator of the SU2 current, so that is quantized, that can't change, but the L2 is the conformal dimension, and that can change. So this operator basically tells you how much the anomalous conformal dimension, how much anomalous conformal dimension you pick up. And just like for n equals to 4, people concentrated on the SU2 sector, and here we do something similar. We concentrate on some boson and some fermion. So the way you should think about it, this is the analog of the SU2 sector for n equals to 4 Supermills, for people who remember these words when they were used 15 years ago. Okay, so what's the idea? The idea is you look at some Mach non-excitation on this VPS state, and you ask, how do these supercharges act on it? So the left-moving supercharges on the left-moving Mach nons turn bosons into fermions and fermions into bosons. That's what you expect. But the idea is that to first order in perturbation, the right-moving supercharges will also turn a left-moving boson into a left-moving fermion into a left-moving boson. But this can only happen to first order in perturbation, because before you perturb, the right movers and the left movers live in different universes. They don't talk to each other. So the idea is that by virtue of the permutation, you're coupling left and right movers together in an interesting manner. Now so for example, you predict that this term is there, and this term is something we can calculate. So this is basically the matrix element of the state on the right-hand side, the bra associated to it, times the operator on the state, and you put in one phi2 is the perturbing field, and you integrate it over Z. That's the first order correction to it. And if you can calculate that, then you can calculate this coefficient to first order in G. So our idea is to calculate this to first order in G. Now, again, this is not a super new idea, except nobody managed to calculate this coefficient. I mean, Governor Ryan calculated in the limit where NW goes to 0, and somehow people never quite managed to calculate it. It is a bit of a complicated calculation, but here is the answer. So you can just do it. I mean, if you have a strong graduate student, you can just do it. And so Beat is a very strong graduate student, so it took us a while, but this is the answer, and it's exact. This is the answer to first order in perturbation. Now, this answer looks like a mess, and I think this is the reason why Shlomo and Rastelli and so on couldn't really see the integrable structure from this. And I think our slightly new insight is that this simplifies dramatically if you take the W goes to infinity limit. So you take the W into infinity limit, which is the asymptotic spin chain limit, where the length of the spin chain, if you think of it as a spin chain, it isn't quite a spin chain, but naively, if you think of it as a spin chain, the length goes to infinity. you want to keep n over w, the momenta, fixed, but take w to infinity. And when you do that, then you see that these things simplify dramatically, and it basically becomes a sine divided by a square root of 1 minus p, where p is always this n over w, this fractional mode number. Okay, so that's what you calculate. Now, this is obviously for a slightly sort of degenerate case because we have a singular Magnon here, and that's obviously not going to be orbifold invariant by itself. So in order to see interesting states, you'll have many Magnons. And then you will also need, in addition to this coefficient, you will also need to understand what happens to the Magnons that are not only indirectly affected by this perturbation. So this perturbation is a G descendant of this ground state. The G gets contracted with the stuff. But even after that has left, the remaining bosons get mapped into bosons, and they're affected by the sigma 2 factor. And the sigma 2 factor basically just becomes momentum conservation, as you would expect. But there is a funny phase that you pick up, and this phase is a bit delicate to calculate. It depends crucially on exactly how you take this large W limit. Anyway, there's a way of calculating, again, this you can calculate exactly, and you can take the large W limit, and you find this answer. Now, so once you've done this and the dust has settled, you realize that to leading order in 1 over n and in the large W limit, you basically get a very simple algebraic relations. The supercharges turn these Magnons into one another with coefficients that depend on p. Now, obviously, you can rescale them slightly, but basically, this is the key relation that you observe. And we only calculate this to first order in G and their higher order in G corrections, which are difficult to calculate, and we haven't attempted to calculate them. Okay, so there's one important constraint which you have to be cognizant of. This is the central term in the old analysis of Niklas Weisert for n equals to 4, that the central extension of p is 2,2/4 has to be 0. The analog of this here is that the left-moving and the right-moving supercharges have to anti-commute with one another. This is not automatic anymore once you've switched on these correction terms. But you can check that at finite W, it's actually identically true. So this being identically true at finite W is a statement that the scheme by which we have calculated this is somehow going off shell because we are not quite imposing the orbifold invariance, is self-consistent because these supercharges anti-commute with one another. So that works out fine. But in the large W limit, this only works provided you choose the correct phase factor for this D coefficient. Remember, for this D coefficient, I'm going the wrong way. For this D coefficient, there is this phase factor which we don't quite know. And one way of fixing that is simply to say that once you move an operator past the operator that inserts either one side or removes one side, you're going to pick up a specific phase factor. And once you do that, the large W limit is central and has a vanishing central extension, i.e. this anti-commutator vanishes. Okay, so I'm not going to want to go too much into detail of it, but the upshot of this is this then allows you to basically write down, using standard integrability arguments, the contribution of an individual Magnon, and you can show that this structure is integrable. You can find the S matrix, and everything fits together in the way you expected it to fit together. But this is now derived from an honest symmetric orbifold perturbative calculation. So this is the analog of what Minahan and Zarembo did for Supang-Mills, where they calculated Supang-Mills in perturbation theory and saw a spin chain and integrable structure emerging. Here, we've done the same thing for the symmetric orbifold. We've seen the integrable structure. We see the analog of that, except somehow for AdS3, historically, the order has been reversed. I mean, for n equals to 4, that was the starting point, and here it's somehow the end point that now that we've believed that we understand this, we can also reproduce this. And this reproduces what people had conjectured before in the integrability community. Okay, so this is good. So what is the slight confusion? Well, the slight confusion is that here in the symmetric orbifold of T4, you have 4 bosons and 4 fermions, and they're fractionally moded. Now you can ask, what do the 4 fermions and the 4 bosons correspond to in AdS3 cross S3 cross T4? And the natural guess is that the 4 fermions and the 4 bosons of T4 correspond to the Magnons of T4. That's a pretty obvious guess. But the string theory lives in AdS3 cross S3 cross T4. It shouldn't just have Magnons associated to T4. It should also have Magnons associated to AdS3 cross S3. Certainly, once I switch on Ramond flux, I go away from this tensionless point, I should see the excitation corresponding to AdS3 cross S3. So where are they? Now, the old answer, the old idea was, and this goes back to Gavin-Ryan, is that they should be associated to the fractional bilinears in the bosons and fermions that define the n equals to 4 generators of the symmetric orbifolds. The T4 theory is an n equals to 4 superconformal field theory. The stress tensor and the supercharges are bilinear in the free fields. And in the W cycle sector, you get fractionally moded modes associated to the n equals to 4 generators, and you would expect that the n equals to 4 generators correspond to the Magnons associated to AdS3 cross S3. Now, this sounds sort of plausible, and it sounds confusing, because in some sense you think you are double counting. I have already taken account of the boson, so why should I also take account of the bilinears in the bosons? Now, obviously, there is an order of limits issue, so I have to be careful. So one question that has always confused me is whether these are really independent, because they're just bilinears of the stuff I've already calculated. Now, at a free point, there's no way of distinguishing between all of these modes, because basically everybody is degenerate. But now that we've understood this perturbation, there's basically an unambiguous way of deciding what the correct picture is. So what is the idea? So let's look at one sector. So let's look at bilinear fermion states acting on a BPS state. So I fix n so that the total mode number is n over W, and A runs over from n to W. So these states are all degenerate before I do any perturbation. And then naively, if you believe what I've just told you, is that each of them will become an eigenvector of the perturbed Hamiltonian with this anomalous conformal dimension, because that is what this mode gives me, and that is what this mode gives me. But on the other hand, this n equals to 4 picture would suggest that that the fractional n equals to 4 mode, which is the sum over all of them, should have an anomalous conformal dimension associated to that. So obviously, there is some tension between these two statements, and we should be able to understand what are the actual eigenstates when I perturb the system away from the free point. So this is what we did. So the idea is you take the system at finite W, you take the full answer at finite W. So remember, I wrote down these exact matrix elements. I calculate L0 tilde minus K30 tilde, which is this anticommutator of the supercharges. And I calculated on the subspace of states that are made from these states. So on this subspace of states, I evaluate L0 tilde minus K30 tilde, because it's the anticommutator of the supercharges, and I have an explicit expression for it, and it's a matrix of size W minus n, cross W minus n. And on this matrix, then I can diagonalize for any value of W, and then I can look at what these eigenvalues look like when I make W large. And what I would say is that this corresponds to a torus mode if it's what I call a short eigenvector, if it's an eigenvector that basically has a contribution only from one of these Magnon states. But if it involves basically all of them, then I would identify it with a long eigenvector, with an excitation associated to AdS3 cross S3. Now, you simply do the calculation, right? Now, it's a precisely defined problem, so you do it and you get what you get. So what you get is this. So what does this mean is, so here we are looking at n equals to 3 and W equals to 50, and here are all the eigenstates, and this is the heat map of the eigenstates. So the color coding is, so up here is the basis elements of the spaces, and the color coding is the value of the coefficient in front of each of these basis vectors. And the brighter the color, the bigger the coefficient, and the darker the color, the smaller the coefficient. So you see there are all these eigenstates, which are basically a linear combination of two. So two of them are degenerate because of the symmetry between psi and psi bar. But there is exactly one eigenstate that's a linear combination of basically all of them. So what you see is that there is basically one mode that's a long mode that you should identify with AdS3 cross S3, and then there are lots of short modes. All the other ones are short modes, where you just get one of these coefficients, or basically two of these coefficients being non-zero. So this is what you find. Now, the coefficient with which this appears isn't quite a constant. So if it was truly the fractional n equals to 4 modes, then it should have been simply the linear combination of all of them with coefficient 1. Now, that isn't quite true. Depending on what n over W is, this curve has a funny shape. but there is always exactly one long eigenvector, and all the other eigenvectors are short. So, and furthermore, this long eigenvector, you can calculate the eigenvalue of it, because when you you solve the eigenvalue problem, you know the eigenvector and you know the eigenvalue. And what you find is the eigenvalue fits exactly with the expectation from the AdS3 cross S3 Markov. So it has exactly the correct dispersion relation that you would have associated with the massive modes associated to AdS3 cross S3. So this is what you find. So apparently, the symmetric orbifold does contain the AdS3 cross S3 excitations, but they are hidden inside the long eigenstates that you get from these bilinear fermions and bosons. Now you can check this a bit further. So here we looked at one sector. So you can repeat this in all the other sectors where you expect one. And in each sector where you expect a long eigenstate, you find one. But there's, for example, a sector where there shouldn't be a long eigenstate, and indeed there isn't. So this analysis is smart enough to give you exactly the correct number of long eigenstates. And the way this works out is that they are exactly in one-to-one correspondence with the old idea for where the AdS3 cross S3 Marknons come from. The S3 Marknons involve the K- modes, the AdS3 Marknons involve the L modes, and the supercharges are obviously the fermions that in some sense involve both. So this basically proves that the old idea of these people was essentially right. The AdS3 cross S3 Marknons come from something that looks like the n equals to 4 fractional modes. It's not strictly speaking the n equals to 4 fractional mode because it has this funny profile, but they are there. They're really independent, and they're independent at large W. At finite W, it makes no sense to think of them as independent, but at large W it does, and that obviously fits together with that this whole intuition comes from the BMN limit, and in the BMN limit you take W into infinity. So in this limit, these modes emerge, and the symmetric orbifold of T4 actually knows about all space-time directions, not just the T4 space-time direction. Okay, so this is the first part of what I wanted to tell you, and I think I'm reasonably in time. Okay, so let me come to the second half of my talk. So what I want to explain to you is an analogous construction for AdS3 cross S3 cross S3 cross S1. And so let me start by reviewing a little bit the painful history of this subject. So the CFT dual of strings on AdS3 cross S3 cross T4 has been agreed upon for many, many years, but AdS3 cross S3 cross S3 cross S1 has been painful because there's been much confusion. So you can describe it by similar techniques as AdS3 cross S3 cross T4. So you have Virasoro times 2 SU2 plus S1. So you know that the dual CFT should be a CFT with what's called large n equals to 4 superconformal symmetry. So this is a superconformal symmetry. You have 4 supercharges, but you have 2 SU2 levels. And the SU2 levels basically correspond to the sizes of the 2 S3s, because you can choose the sizes of the 2 S3s independently. You get 2 levels in the dual CFT of the 2 SU2s, and there is an n equals to 4 superconformal algebra that has R symmetry SU2 plus SU2, which is SU4, which makes a lot of sense for an n equals to 4 superconformal symmetry. And that's the CFT, the symmetry algebra of the CFT dual. And obviously, you know what the levels of the SL2 and the SU2s are. And this is just a familiar relation that the radius of the AdS3 is fixed in terms of the radii of the 2 S3s. And that's the sort of CFT avatar of that relation. Now, if you're a simple-minded person, you would have thought, it's very simple what the CFT dual of AdS3 cross S3 cross S3 cross S1 is. The principle is monkey see, monkey do. So what's this principle monkey see, monkey do? You say you look at AdS3 cross S3 cross blah is the symmetric orbifold of blah. So therefore, AdS3 cross S3 cross S3 is the symmetric orbifold of S3 cross S1, right? Because that's the leftover after you've stripped off AdS3 cross S3. So S3 cross S1, if you write it in slightly more fancy language, is what's called S kappa. This is a certain n equals to 4 superconformal theory, large n equals to 4 superconformal theory. So the most naive guess is that the CFT dual is just the symmetric orbifold of S kappa. And this is indeed what I think various people proposed. But then there was this paper by De Boer, Pascanucci, and Scaderis, in which the supergravity analysis was done, and many more BPS states were found in supergravity than are actually present in the symmetric orbifold of S kappa. So people abandoned this and said this can't possibly be the right idea. Now, this supergravity analysis is very delicate, and as it turns out, when we redid it many years ago, we found that the surplus BPS states that you found are not actually BPS once one analyzes it more carefully. And you find that it actually matches the symmetric orbifold of S kappa if one of the levels is 1 and the other one is kappa plus 1. And so at least the BPS spectrum matches, but the question is this an exact duality on the same level as AdS3 plus S3 plus T4? And I think this was always confusing because the SL2 level is now at a funny point, and it wasn't clear whether this is just on the same moduli space or an exact duality. Well, so K plus is 1, K minus is this, and then K is fixed by this relation I wrote down earlier, right? The K of the SL2 is fixed in terms of the Ks of the two SU2s. So once you fix this, it fixes the K. But as it turns out, this K is going to be less than 1, and that causes some problems. Well, kappa is an arbitrary integer, yes. So it could be 0, 1, 2, 3, 4. Because it's the level of the S kappa. S kappa is basically, S kappa is basically the level of the SU2 inside this. So this algebra is basically SU2 level kappa plus 2 plus U1. So that's what this such S kappa theory is. So kappa has to be an integer starting from 0. Right. Yes. Right. But as I'm about to explain, this is not the exact duality. So this is what. So this is something that works on the level of the BPS spectrum. But the proposal I'm going to make is for a slightly different exact duality. It's not going to involve this. It's going to involve a slightly different background. Sorry, S1? Well, the S1 radius is whatever it is, right? The S1 radius goes along for the right. So the S1 is the S1. I mean, you can choose it to really whatever you want. What's critical is the radii of the two S3s relative to the radii of the AdS3. That is sort of hardwired. Okay, so this is where this subject stopped. And I mean, I tried to prove the duality for this background, and I failed miserably for many years. So at some stage, I mean, Yao was saying yesterday the wise words that if you get stuck, then eventually you should change course. So this is, I mean, at a much, much lower level. Obviously, I'm kissing the feet of giants and so on. But at a lower level, this is my experience here. I tried for many years to prove this in the same way we proved AdS3 plus S3 plus T4. I failed miserably. And then I had a smart student or two smart students that did something different. Yes. I think so, yes. That's what it looks like. At least for, I think, again, there is subtleties. I think that's true if one of the levels is 1 and the other one is K plus 1. So independently, my partially former and current students, Bob and Witt, have been sort of trying to sort of understand this sort of from a more path integral perspective, trying to sort of demystify this NS background. And they developed some technology and some intuition. And by looking at what's called this near boundary limit, they managed to reproduce what Lawrence proposed for these NS backgrounds with flux bigger than 1. So somehow they're doing the right thing. But in that framework, you can sort of generalize it to basically arbitrary backgrounds. And what that analysis suggested is that the CFT dual of AdS3 cos S3 cos S1 should be the symmetric orbifold of an n equals to 1 linear dilaton, which is basically what you inherit from the AdS3. And the rest just goes along for the right. And in general, you have a 2-cycle deformation. So this is for K bigger than 1, this is the deformation which Lawrence proposed to describe the CFT dual of the pure Lewis-Schwartz background. So in general, that will happen here. But this is basically what follows. If you just follow the elite, I mean, you listen to them and you say, what does it predict? That's what they would tell. Okay, so now this is a linear dilaton, so this is complicated, but you realize that if the AdS3 factor is at level 1, and this is the answer to Way's question, so if the SL2R is at level 1, then this linear dilaton actually just becomes C equals to 1. So in general, it has a background charge, but the background charge goes away if this SL2R factor is at level 1. So then this just looks like one free boson and one free fermion. And then because of this relation, you can only make K1 if both K plus and K minus are equal to 2. 1 is equal to a half plus a half. It's one of the easier equations in this talk. And so at level 1, you basically, the two SU2s are at level 2. But you remember, at level 2, this is the supersymmetric level. So once you decouple the fermions, that means the bosons are at level 0. So they disappear and you just retain the fermions. So what this suggests is that the dual should be R0, which is what this n equals to 1 linear dilaton is, plus what you have from the S1. And then from the S3 cross S3, the only thing that survives are 6 fermions, which together with the 2 fermions from here give you 8 fermions, which basically looks like the symmetric orbifold of S0 squared. Doesn't look like the symmetric orbifold of S0, it looks like the symmetric orbifold of S0 squared. But at this stage, you're not sure whether there is a perturbation or not. And in fact, there is a very concrete way in which you can think about it. You see, you have SL2R at level 1, you have SU2s and U1s. The SU2s at level 2 just become 3 fermions. So you get 3 plus 3 fermions from here. You get 1 fermion from here. This gives you 7 fermion and 1 boson. And this, you have 3 directions, but the physical state condition eats 2. So you retain 1 boson and 1 fermion, the radial boson and the radial fermion. So the total number is 8 fermions and 2 bosons. And there is, in fact, the worldsheet theory one can write down, which is you keep all the continuous representations, and it's modular invariant, and you would, on the level of the spectrum, that just reproduces this theory. Now, in fact, this is something which in the early days of this subject we also already observed, but somehow subsequently we felt this was slightly misguided and we should be at a different point. And at that stage, it wasn't clear whether the correlators would work or not. But this is the proposal. The proposal is that the correct duality is not when one of the SU2 levels is 1, but when the SL2 level is 1, and the SU2 levels are 2. And a nice side effect consequence of this is that this is something you can actually do purely in the NSR description. Because once you're at level 2 for the SU2 Westermino-Witten models, you can decouple the fermions, and it's a bona fide NSR description. So unlike AdS3 cross S3 cross T4, where you have to go to this complicated hybrid formalism, which nobody really knows how to deal with, here it's conventional Green-Schwarz-Witten CFT technology. You just do NSR, nothing fancy. Okay, so this is the proposal. Now, one nice feature of this is, this is an underappreciated fact, which I won't tell you who, but I recently mentioned this to somebody and the person was shocked and said this can't possibly be true. But you know, when you study AdS3 cross S3 cross T4 on the worldsheet for any value of k and you calculate the BPS spectrum, it doesn't actually match the BPS spectrum of the symmetric orbifold. There are gaps. Every kth BPS state is missing. Now, obviously, for the k equals to 1 theory, everything matches exactly. But for generic AdS3 cross S3 worldsheet theories, you are not getting all the BPS states of the dual CFT. Now, for this example, you do get actually all the BPS states. So that means it's maybe a slightly better chance of being an exact duality. It can only be an exact duality if you get all the states. You can't have gaps if you don't match. So this matches actually exactly, and this maybe suggests that this duality is exact without any perturbation. You don't have to switch on this funny 2-cycle twisted sector perturbation of Lorentz. Now, this was controversial. I think Kutasov wrote a paper and said this can't possibly be true because there must be this 2-cycle perturbation and so on. So I started to think about how I would be able to prove it. And what you would have to prove it is by showing that the SL2R level 3 theory, which is what survives after you've decoupled the fermions, has actually, this is a purely bosonic Westermino-Witten model, and in order for this to match the honest symmetric orbifold, it must have correlators that have the same localization property as the original AdS3 cross S3 cross T4 store. Now, we could never show this on the level of the bosonic Westermino-Witten model. We needed a full hybrid superstring machinery. But if this proposal is true, what it predicts is that the SL2R level 3 Wessel-Witten model has correlators that localize so as to produce the covering map structure of the symmetric orbifold. Now, this is in contradiction with what people believed, because Andrea Day and Lawrence Ebert, they studied the Wessel-Witten model corresponding to SL2R generic level K, and they showed that for generic level K, there is only one solution, and the solution doesn't have delta function localizing features. It would sort of be smeared out, i.e. the dual CFT can never ever be a symmetric orbifold. It would always be a symmetric orbifold perturbed by something. But since K equal to 3 is maybe a very special point, I convinced Lawrence that we should look into this more carefully and see whether there is actually another solution at K equals to 3 that would exactly correspond to have this localizing structure and thereby de facto prove this duality. And so again? No, sorry, I mean, this is now bosonic. So this comes from SL2R supersymmetric at level 1. After you strip off the fermions, it becomes SL2R level 3. So this is the bosonic SL2R level 3 Wessel-Witten model. But once the dust has settled, in order for this to work, this SL2R, the bosonic SL2R level 3 Wessel-Witten model must have localizing solutions. Otherwise, this proposal I made with Witt can't be true. Now, what we did is we simply found a set of correlators that localize. So we made this ansatz. I mean, this is inspired, obviously, by their previous work. But we made this ansatz, which is, I'll explain to you the pieces of it in a second. But we checked that this actually solves crossing symmetry, and it's a solution of the Knizhnik-Zamolodchikov equation. So it basically is essentially fixed by this. So this is a solution. We checked it for n equals to 4. It's almost certainly a solution for all of them. And it's a very unusual solution of the SL2R Wessel-Witten model because, you see, basically it has two ingredients. It has stuff that comes from covering maps. So there's a sum over all covering maps. There are factors that come from the combinatorial factors that are involved in the covering map. And it delta function localizes to the positions where the covering map exists. And the rest of the correlator is essentially just a free boson correlator, as you would expect. So this SL2R level 3 Wessel-Witten model has a remarkable set of consistent correlators that satisfy crossing symmetry and are a solution of the Ward identities, in particular the Knizhnik-Zamolodchikov equation. This is a different solution than the generic solution that Andrea and Lawrence found. The generic solution doesn't delta function localize, it has tails. This is a solution that has only contributions at the configurations where the covering map exists. The spectrum is multi-line variant. So this spectrum only it only involves the spectrum that Witt and I proposed for the dual CFT, i.e. only the continuous representations, no discrete representations. So there are no poles. There are no additional poles that generate additional states. So it closes entirely on the continuous representation. So this parameter, so I may have gone a little bit faster with it. So the continuous representations of the form half plus IS, and this S becomes the momentum of the free boson that appears implicitly there. And the only thing you have to do is to let S run over all real values, not just over the positive half. You introduce this to be over all real values. And then these correlators close on the spectrum, are crossing symmetric, and satisfy the Ward identities, i.e. the Knizhnik-Zamolodchikov equation. So this is, I mean, in my opinion, this is an even more well-established solution of this Wessel-Witten. This is a more established Wessel-Witten model than any other Wessel-Witten model I know, because you can write down a closed formula for all endpoint functions. I mean, in general, solving Knizhnik-Zamolodchikov equations is hard. Here you can write down all of them. And you can check crossing symmetry, and you can check Knizhnik-Zamolodchikov, and they just satisfy all of it. So I'm totally convinced that that's a consistent theory, because I've checked it much better than most of the CFTs I've worked with in my life. So this is a remarkably simple Wessel-Witten model, but it basically immediately proves the duality, because the spectrum matches. And now the fact that you have this delta function localization means that the correlators on the worldsheet you can write as sums over covering maps, and the covering map data organize themselves into reproducing exactly the correct coefficients to reproduce the symmetric orbifold correlators of the dual CFT. So this is, I think, as well established as a duality as AdS3 cross S3 cross T4, but it has the added benefit that now this is done purely NSR, no hybrid, and it seems remarkably simple. It seems like the avatar of all of these dualities. And furthermore, so this is basically what follows from this. You see that the CFT dual of this is exactly one compact boson. That's the boson associated to the S1. The one non-compact boson, that's the radial direction of AdS3 with momentum S and 8 fermions. And that's exactly dual to this background with 2 units of NS flux through the 2 S3s and 1 unit through the AdS3. But actually, if you take this seriously, it predicts much more. It predicts things you wouldn't have believed should be true. It predicts that bosonic string theory on AdS3 at this specific point where you choose that solution for the Wessel-Witten model types any theory at c equals to 17. So this has c equals to 9. So 9 plus 17 is 26. So critical string theory tells you the rest wants to be a c equals to 17 CFT. This is going to be dual to the symmetric orbifold of R cross X, where X is the c equals to 7, your favorite c equals to 17 CFT. And the radius has momentum that's exactly a half plus IS spin of the SL2R representation. And it's more or less a triviality to see that the spectrum matches and the correlators match. So this is as well established as any of these dualities. So it's remarkable that you get this, what seems to be at this very, very special points for AdS3, you seem to get a whole zoo of dualities, and they don't involve any supersymmetry at all. It doesn't seem to hinge on supersymmetry because once we've understood this for the bosonic Wessel-Witten model, you don't need supersymmetry to get there anymore. This is seemingly an exact duality. It doesn't involve supersymmetry. Maybe it still involves integrability. I don't know. But it's a very generic statement, and it more or less follows automatically once you have this very concrete fixation of this SL2R level 3 Wessel-Witten. Okay, so my time is coming up, so let me conclude. So there are 2 things I explained to you. I explained to you the perturbation, the deformation of the old AdS3 cross S3 cross T4 duality by switching on Raman flux. So in particular, we found the symmetric orbifold is indeed integrable, and we could unambiguously identify the space-time Magnons associated to AdS3 cross S3, and these are the bilinear fractional Magnons, and that sort of confirms the old picture of Gavana-Ryan and Gomez model in Strominger, except it's slightly modified because it isn't strictly speaking the n equals to 4, the fractional n equals to 4 generators. And then the second one is that I explained an exact duality between string theory and AdS3 cross S3 cross S3 cross S1 with 2 units of NS flux through the S3s and 1 unit through the AdS3 factor. That's exactly dual to this symmetric orbifold of what looks like S0 squared. And for that we've basically established, I believe. And this SL2R Wessel-Witten model analysis basically suggests that this must generalize to all sorts of backgrounds, in particular, essentially any bosonic string theory. And I think it'll be interesting to explore this further. Maybe the integrability is what really controls this. I mean, supersymmetry doesn't seem to be relevant here. I mean, I think this is the maybe small or big surprise, however you want to think about it. Supersymmetry doesn't seem to be at all relevant in order to make this work. So AdS3 CFT duality doesn't care about supersymmetry. So I think this is interesting. There is probably something to be learned here. And with this, I thank you for your attention.
Any question or comments?
There are also some related backgrounds that they have instead of S3 and S2, like AdS3, S3 plus S2. Do you think you can have dualities for those as well?
So this is meant to be a critical string theory. Yes. So you choose AdS3 cross S3 cross S2.
Yeah, and then you have
plus something else. Or?
Something.
Well, I mean, now it looks as though. I mean, I'm still sort of getting used to the idea. But once you strip off the fermions, right? I mean, this is basically, the fermions typically just go along for the ride. So if I'm not manifestly preserving the supersymmetry, this duality basically tells me what this is for any of these macros, right? I just think of it, if the bosonic SL2R is at level 3, then I can tell you what the dual CFT is. So if you give me some background, I strip off the Fermi and do the usual stuff. If the SL2R level once the dust has settled is 3, then I think of the rest as being X, and then I can tell you what the symmetric orbifold of it is. Now, whether supersymmetry is preserved in this, whether this is a superconformal field theory, is not so obvious. Right, so, but in principle, you would think that this basically tells you in all of these examples, this only works when this level turns out to be, so this is the tensionless regime, right? It's always the tensionless regime. It's always this being level 3, giving you directly a symmetric orbifold. As long as this happens, this tells you what the CFT dual is. And it should work with supersymmetry, without supersymmetry. And you can always just ignore supersymmetry and treat it as a bosonic theory, and then this will tell you the answer.
Yeah.
Does the short string sector also disappear?
Yes, it disappears. There's only long strings. I mean, these correlators don't have any poles. They are just, they look like just free bosons, right? I mean, you're not seeing anything funny. So P is basically the S that I described, a half plus IP or a half plus IS. So this is only defined for operators associated to momentum, in this sector, but you don't see any poles. So there is no, you're not generating discrete representations in the process. They're totally decoupled. But this only works at level 3. This only works at level 3 somehow. Yes, exactly. So the picture is at level 3, there is a duality that doesn't involve this sigma 2 perturbation. It's an honest duality to a standard symmetric orbifold because the correlator just localizes as you would expect it for a standard symmetric orbifold. But as soon as you go away from k equals to 3, it will not localize. And then in terms of the dual CFT, you will need all of these 2-cycle perturbations. Yeah, that I haven't thought, yeah, maybe I should look into that carefully. But I know what I've done. Yes, the claims are slightly different. I mean, this I'm pretty confident is correct. And yeah, so for AdS3, cos S3, cos S3, cos S1, because it's a symmetric orbifold S0 squared, this theory is remarkable in that it doesn't have an exactly marginal operator. Because the ground state of the seed theory is too high. The 2-cycle twisted sector operator is already too high to give you an exactly marginal operator. So it's a bit funny. It's a sort of an isolated point, but at this isolated point, it just works.
So if there are no more questions, let's thank our speaker again.